Hello, I'm Chen Li. In this talk, I will introduce our paper Federated Learning with Data-Agnostic Distribution Fusion. Federated learning is an emerging distributed machine learning paradigm that aims to build a global model based on models locally trained by multiple clients. Local data distribution heterogeneity is a main problem in federated learning. When training data distribution at each client is much different from each other, it's hard to generate a global model performed well on all clients. For one model federated learning, centralized training with complete dataset is a performance upper bound. Our main purpose is to better imitate centralized training. We assume global data distribution exists and composed of several virtual components. Each client partly belongs to these components. We can infer local data distribution and use the distribution parameter to calculate best aggregation weights for client models, mitigate the accuracy drop caused by distributed training. In this paper, we propose to replace the sample count-based loss function with a component fusion-based loss function. It first reconstructs models and generates models from M virtual component with weight B, then aggregates this model with weight pi. Define the learning problem in a distribution fusion perspective. With the privacy concern of federated learning, we need to infer local data distribution without access real data. We develop a variational autoencoder to achieve this goal. Normalization layers in neural network models contains distribution information and widely used. They can be used to infer local data distributions. The input of variational autoencoder are extracted from these normalization layers such as batch normalization or group normalization. The variational autoencoder will then use the input statistical information to infer local data distribution. More precisely, we use Gaussian mixture model to fit data distribution, and the variational autoencoder can infer the distribution parameters. It works as a bridge of distribution and parameters. With input dk, the encoder phi can generate parameters for distributions. Notice that we use Gaussian mixture model to fit local data distributions. The element of ck is a 0-1 variable, determining whether a client belongs to one virtual component. It can be sampled from a Bernoulli which is parameterized by lambda k. The conjugate of Bernoulli is a beta distribution, so lambda k can be sampled from a beta distribution. Bk is a real number determining weights of client k in each virtual component, so it can be sampled from a Gaussian distribution. The weight of each component pi k can be computed with a softmax. Decoder theta will reconstruct dk with the latent vector zk. All this procedure shows how variational autoencoder works in our algorithm. Directly infer parameters of beta distribution is hard for conventional variational inference methods, so we approximate the posterior beta with the Kumarasurami distribution, as the slide shows. For the 0-1 allocation vector ck, we use the Gumbel max trick to draw samples from a Bernoulli distribution with binary probabilities. We validate our proposed Fed-Fusion algorithm on MNIST, Fashion MNIST, CVPR10, and Sentiment 140 dataset, use ResNet 18, DenseNet 121, MobileNet v2, LeNet, BiISTM as backbone models. For single model scenario, we choose FedIVG, FedProx, FedGN, FedMA as benchmark. For multi-model scenario, we choose FedSam, IFCA, FedCluster, FedGroup as benchmark. Figure here shows the accuracy and loss results for training different models on different datasets. Clearly, Fed-Fusion has the lowest loss and converges the fastest among all algorithms, and it reaches higher accuracy in a shorter period. In this table, we choose final accuracy of all these algorithms after convergence. Since clustered and personalized FL methods output multiple models, we choose the average results of all these output models. We repeat each experiment for 20 rounds and calculate the average result. Fed-Fusion achieves the highest accuracy among all compared algorithms, improving the global model's accuracy up to 12%. Here we give the visualization of Gaussian mixture model for MNIST dataset and CVPR10 dataset. We plot the original distribution by projecting the data sample of the full dataset from all clients to a 2D plane with TSNE, and apply the proposed algorithm to infer the parameters of the distribution fusion model, based on which we generate the same number of synthetic data samples as the original dataset. According to the figure, the inferred distribution looks very close to original distribution, which implies that the federated server can well approximate the global distribution parameters without accessing the local data. Furthermore, we calculate the mean absolute error of the statistical parameters compared to a centrally trained model based on a global dataset. It is shown that Fed-Fusion has a much lower bias in the statistical parameters than that of other algorithms, which means that Fed-Fusion provides a better approximation to the global data distribution. Further experiments on learning rate eta and client count shows the robustness of Fed-Fusion. With varied hyperparameter settings, Fed-Fusion yields the highest test accuracy and lowest performance drop among all compared algorithms. That's it. If you want more details, please refer to the paper. Thank you for watching.